All right, so week 4, ELEC2141. Just to recap on what we've done in the first 3 weeks of the lectures. In week 1, we talked about number systems, we introduced binary. Week 2 and 3, we started introducing combinational logic. We talked about Boolean algebra and then circuit optimizations. Now, all those 3 weeks, essentially, we lay down the fundamentals to what we're really going to be doing in this course, which is the design part. So what we'll do in today's lecture is introduce a couple of design problems. I will go through how do we go about designing an actual circuit or solve an actual problem using the knowledge that we gained in the first 3 weeks of the lectures. I will, in the second hour today and on Friday, I will introduce to you some new concepts or building blocks that we used a lot in combinational logic design. And then in the following few weeks, we will start introducing sequential circuits and then take it to the next level. So let's talk about the design procedure. So what do we even do in this course? You'll probably go out to the real world and you'll work for some digital company because you all love this subject and that's what you'll do. And then your boss will come up to you and say, here's a problem. Our client wants you to build a circuit that does so and so. Go for it. Now, usually what you will get in the real world is some verbal or some written expression of the problem. And that's what we call the specification, where the client or your boss or whomever will tell you what they want. Now, those specifications will not always be full. It won't tell you how to go about implementing the circuit. It may as well not actually cover all the different options that, or all the different inputs that your design will handle. It will usually cover what the client's interested in and what the inputs will be to your system, what the outputs should be from your system. But it usually may or may not specify inputs that may not happen or inputs that they don't care about. So once this problem is handed out to you, you have to formalize the problem in terms of truth table or in terms of engineering terms. So something very specific, very unique that you can actually work with and build a circuit. So this is what we call the formulation process, where you take this English description of a problem and then you say, okay, these are my inputs, what am I doing with them, how do I relate those inputs to the outputs. Usually from the formulation process you end up either with a truth table that relates the inputs to the outputs, or you may end up with some Boolean expression that relates the inputs to the outputs, and this is something you can actually work with. Now, we know how to work with truth table. We know how to start implementing circuits once we have truth tables. These are stuff that we've done. So the next step, once you have the truth table or the Boolean expression, you apply some optimization to it. Now, when you do optimization, it really depends what you're optimizing for. If we're optimizing for speed, we will usually try a 2 levels implementation, and for that we have the Karnaugh maps that will usually give you very good result for optimization. If you want to optimize for gate input cost, you might go to multiple level optimization. So again, depending on what the specifications are, there's different types of optimizations you can have, but you do it at that stage. So, steps 1, 2, and 3 are stuff that we mostly talked about in the first 3 weeks. What we will look at today, as well as some other things, are steps 4 and 5. In step 4, we do what's called technology mapping. So after you design your logic in a logic diagram or a circuit diagram, then you have to implement it somehow. Now, we said usually with CMOS technology, which is a very popular technology, the preferred way to do things is using NAND gates. Different technologies will give you different ways of doing things. I will concentrate today on technology mapping for NAND gates because this is the one mostly used. But in step 4, it's actually a general step that will transfer whatever you came up with to the technology that's available to you at the time. In step 5, verification, once you've done the transformation, so you came up with some technology mapping, you now want to verify that what you came up with actually matches the original specification that the client gave you. Because, you know, you might have made mistakes along the way. Maybe your truth table had some error in it. Maybe while doing technology mapping, you forgot something in there. So step 5, verification, verifies that, yes, this is what the client wanted. Now, this is a step that we always in practice do. We always test our designs. And usually we do it before we actually implement it on a chip or implement on, if it's an FPGA or whatever we implemented. Just before it's easier, just because it's easier to actually address those problems during the design process than after you implemented them and then you realize your problem. And then you have to step back a whole lot more steps. So, as I said, I will concentrate on steps 4 and 5 now. And if we're talking about technology mapping, I want to introduce to you how we map into NAND gate. Last week on Friday, I very quickly showed you how we go from using OR gates to NAND gates, and I told you about pushing the bubble. Now I want to introduce an example of how we're doing it in real circuits and how it is actually handy. So, for example, we have some function specified here, and we want to implement this as a NAND-only implementation. What we will do, and I will step through it, we start off with actually drawing the circuit as it is given in the function here. Yes, you could actually do further optimization on this one, but I do want to implement it as given because it'll give us some good example how to do technology mapping. Okay, so now we start off with drawing the circuit. So I will start with the AND gate there. I will now use this AND here. Sorry. So from the AND gate there, we have the term A and B. For the second term, we need the inversion of A and B, so we will pass it through an inverter and then end it with the C. So from here, we will get this whole term here. Similarly, we'll have another AND gate that will take A and B, not A and B, and it will also take not D in. So if I had D available, I will pass it through an inverter and pass it through this AND gate there. Now I also probably have a signal E coming through. That's for the last term. I don't actually need to do anything with it. And now I came up with all the 4 terms, which are now going through a massive OR gate. And this will be my function f. I'll just write the different signals just so you can actually see them. This will be maybe not D. This will be E here. And then the function f will just be the OR of the whole thing. Now, in order to convert this to a NAND-only implementation, I'm using the trick that I know that an OR gate can be converted into a NAND gate if all of its inputs are inverted. So remember we said if we see something that looks like this, this is essentially a NAND gate. So I will start adding bubbles to the inputs of these OR gates. Now, anywhere that I add a bubble at the input, I need to counter this bubble on the other side. So in that way, I don't actually change the function. I don't actually change the expression for the function. So I inverted this input here. I have to invert it on the other side. Now, the inversion comes from here. So once I invert there and I invert it back, the input to the OR gate is unchanged. The problem is that once I inverted this output here, the signal that goes through this inverter here is also the inverse of A and B, and not just A and B. So I have to account for this by putting a bubble at the entrance to this inverter as well. In a way, I'm just turning it into a buffer, or something I can actually cancel out later. So I just want to make sure you know what I've done here. So if I've inverted the output here, I do need to account for it in all the places where this signal will now propagate to. In a similar way, which is slightly easier now, I put an inversion bubble there, and I counter this inversion bubble with an inversion bubble at the output of the AND gate. Similarly, the input here and the bubble here. Now with the signal E coming in, I still want to invert it because I need to invert all the inputs. I need to invert the signal E, so I'll just add an inverter on this line. So I'm inverting E and then inverting it again. Now what really happened is that I can convert this into a NAND gate, so this will just become one big NAND gate with 4 inputs. All these ones are now NANDs already. Can you just close the door, please? These became NAND gates already. Inverters can be implemented using NAND gates, and we showed how. You just tie the 2 inputs together. And what I end up with, essentially, is a NAND-only implementation. Now, this process can be applied to any circuit that you have that already is using inverters and then ORs. So in last week's lecture, we said we can convert any circuit into NAND only, and this is the easiest way to do it. You could actually do it from the expression directly using Boolean algebra. Using bubbles in a graphical way makes it slightly easier, but if you're happy with doing it in Boolean algebra, no worries there. Now, if I ended up with, let me just see. All right, next slide about verification. If I want to verify this circuit, actually I will go to the next slide. Then I ended up with a circuit that looks different than the actual function there. I want to verify that this actually still implements the same function. Now there's a couple of ways you can do it. If the circuit is fairly simple, and this counts as a fairly simple circuit, it only have 5 inputs, and it's a fairly small circuit, then you can pretty much work back. Go back to the circuit, and then deduce all the signals at the different nodes, and then come up with an expression which will look different to the one up there for the function f. Well, it will look different, but it should do the same function. Then what you do, you take your original function f and deduce the truth table for it. You take the new expression for the function f that you derived from the circuit, and then you pretty much compare the two. If the two match, then great, you've got a matching design, and you know that you came up with the right circuit for the NAND only. Now, if we do have more complex circuits, and in reality the circuits will be more complex than just this, Usually we'll use computer simulations, and these are the kind of stuff you do in your lab, where you'll write a test bench Verilog code that will run all the possible inputs to our circuit. We will define what the outputs should be, and then the software can already run the test through our circuit and then compare it with what it should be, with what the result should be. If there's a mismatch, then the software will alert us, and then we can go and try and debug of what's going on. So that's sort of the way to go about doing this. What I want to show you now is an actual example of a design problem. So we might get a design problem that states, design a BCD to XS3 converter. And then it goes and explains an XS3 code for decimal digit. We know what BCD is, yeah? It's just the digits 0 to 9 in binary. The XS3 code is the same value as the binary plus 3. That's all there is to it. So in order to implement this, we have to come up with, these are the English specification, we have to come up with the formalization for the problem, usually in terms of truth table. Now we know that for BCD we only have the inputs between 0 and 9, so this is what we'll worry about. BCD codes always have 4 bits to them. So let's call those 4 bits A, B, C, and D. Now we will put all the possible combinations for those digits. So I'll very, very quickly write the corresponding binary or the BCD for those digits. Four, 5, 6, 7, 8, and 9. Now, these will be our inputs. We do need to have some sort of an output to the circuit. Now, given that XS3 codes are just those numbers here, plus 3, we can tell that those outputs are going to be 4 bits as well. So we will call them W, X, Y, Z. And now we have to find the mapping between the codes here to what the outputs are. Well, by definition, if the code was the number 0, we add 3 to it. That will be the output. If it was the number 1, we'll get 4 as the output. And, you know, continuing this logic, then we're going to have 5, 6, 7, 8, 9, 10, 11, and 12. Now we have a truth table that matches the inputs to the outputs. The way to look at this now, how do we actually build a circuit for this? Because this circuit has 4 outputs, is we can think of each one of those bits as a function of each one of the W, X, Y, and Z as a function that takes 4 arguments to it. So treat each one of those columns as its own function, and the arguments for this function will be A, B, C, and D. Now if we wanted to optimize it for 2-level optimization using corner maps, then we know that we must use all the possible 16 combinations for the 4 bits here. So what do we do with combinations 0 to 15? Yes? The icon is on. You know, I can hear it, but it's not doing much. Trust me, I'm very odd in here as well. Temperature-wise. So for those, For those input combinations from 10 to 15, well, we assume that they're never going to happen because this circuit only takes BCD. So the outputs will be don't care. So anything there will be marked as don't cares. And then anywhere in the corner maps that these values will come up, we'll just put X's. So we formalized the problem. Let's start implementing it. Now, as I said, we need to treat each one of those, and this is just a nice version of what I just handwritten. We need to take each one of those functions here and deduce its own corner map for the function. So we'll start off with W, and yes, so we'll go one by one. Try to do it quickly. Going through the values for W, I know that for places 0, 1, 2, and 3, then 4, so 0, 1, 2, 3, and 4, we've got zeros, and then for 5, 6, 7, and 8, and 9, we have ones. Now the rest of them, the ones that are not here, we said are going to be don't cares because they should never happen, and don't cares will actually help us optimize this corner map. In later lectures, we actually talk about what do we do when we have don't care conditions, and do we always want to use don't cares, or do we want to force them into some values? For now, we'll just use don't cares because it is actually, it does simplify our function. Now, to try to optimize this, I could use the don't cares to come up with the largest groups possible. So these ones here, I can circle the don't cares as well. For these ones here, I can't make a group of 6. It's not allowed. I must do either a group of 4 or 8. There's no way for me to do a group of 8 for these ones, so I will use 2 groups of 4 for these ones. And then I can read the values. So W, I will start with the largest group, will just be A, which is the large group. Or, what do we have? This group here, which is BC. Or the group in the middle, which is B and D. Now, I hope everyone's pretty fluent with working with corner maps now after solving this week's tutorial. There's plenty of questions about corner map. If not, please practice it. So we came up with an expression for one of the outputs. Now, same story for X. So I'll read it as 0, 1, 1. 0, 1, 1, 1, 1, then 1, 2, 3, 4, 0, 0, 0, 0, 1 for place 9, and don't cares for everywhere else. Now, just a little note here, if you're observant, then you realize that the don't cares for the W are in the very same places as the don't cares for the X function. Which makes sense because the places in the corner maps are the places that correspond to these combinations here. And they will always fall in the same place. So later when I deduce Y and Z, they will be in the same place as well. Now, let's come up with the optimization for this one. I can circle this one here. And then again, I've got the problem of 3 ones next to each other. I can't actually group them together, but I could group 2 of them and wrap them around with the don't cares on the other side. Similarly, I will do this one. And then I got all the ones covered. Those don't cares that I didn't need to use, I didn't use. I just left them as they are. Those don't cares that actually helped me, I did use them. And this will come to x being the one up there is B not C not D. And then the group here is B, sorry, yeah, not B and C. And we have node B and D. So the bottom group and the middle group there. To finish it off, the one for Y. 1 0 0 1 1 0 0 1 1, then 1 0, and the don't cares. This time around, I can probably find one group here and one group here. Which will give me an expression CD or not C, not D. So CD is the bottom one, not C, not C, not D. Top one. And then for Z, the last column here, we have 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0, then 1 0, and don't cares, which actually gives me a nice grouping in this case, because I can now group all these ones and wrap them around and come up with only one group for the whole thing. Now, you know, it took us a bit of time, took me a bit of time to do it, but this is what you do when you solve a real problem. You actually have to find all the expressions for all the different outputs. So these are the expressions I came up with. Now, what if I tell you I don't want to optimize it for 2-level, I want to optimize it for, say, gate input costs. So I want some multi-level optimization. So we know that to do multiple level optimization, we'll start off with trying to factorize the expressions. So W might become A or, and I can take the B out, factor C or D. I can do the same thing with those not B's here and come up with B, not C, not D, or not B, C or D. I don't think I can optimize Y's and Z. Oh, I can't factorize them any further. But now if I'm trying to decompose those functions, then I can see that I've used C and D here. I've used C and D here, so that's already giving me some clue that this is a common term that I might want to calculate once and use it several times in the circuit. So I will define some signal T, and I will call it C or D. Now, because I'm very observant, I also realize that the complement of T using the Morgan will be not C and not D, which comes up in function Y. And I know that once I calculated T, in order to come up with the signal needed for function Y, I won't actually need to pass these through inverters and an NAND gate, but I can just invert the value of T once I calculate it. And then I can rewrite my functions in terms of T. So W will become A or BT. X will become Well, I've got the node C, node D up there as well. And I said I can use the node T. So it'll become B node T or node BT. What gate is that, by the way? XOR. So as I said several times, when you see this expression, immediately you should think XOR. So this will come up quite a bit. Just remember that. With Y, we have C, D, or node T. And Z is just what we had before, which is node D. Now, I'll save you the agony of me drawing the whole thing. So I will just use something I prepared earlier, where you can see the signal T is just here. We calculated C or D, and we fed it through here. So this is the node that will be called T. And we have those four outputs, W, X, Y, and Z, corresponding to the equations we came up with up there. Now, just looking at this circuit, taking a step away from this specific problem, I want to talk about drawing the conventions when you draw circuits. When we have signals, for example, have a look at this node here. I'll erase the arrow, but around this area here, we have two wires crossing each other, but they're not actually connected to each other. Now, a lot of times in electric circuits, you might see something like this. I'm not a huge fan of this notation, but it helps to show that the two lines are not actually connected together. Now, usually, like in this case here, as long as they cross each other and there's no bubble there or no dot, then that means the lines are not connected. The problems start when you do want to connect them, and then you might have something that looks like this. But then, because those dots are fairly small, then sometimes it's easy to miss them, or sometimes it's actually confusing to think that two lines that should not be connected, like here, are connected, or two lines that shouldn't be connected, well, two lines that should be connected are not connected. Therefore, what I like doing when I draw circuit diagrams is to decide to never have this style of connection where I need to connect four things together. If I need a signal, if I have a line here and I need a signal to come in or out from here and another one from the bottom, I will separate them and I will draw something like this. Then there's absolutely no confusion because you know, even if the bubbles are small or missing, then you'll never have something that just looks like this if the lines are not actually connected. So that resolved this confusion, and this is the convention I will use in this course. So places like here, for example, where I could have just drew the line straight down and then put the dot here, I decide against it and I separate those two apart. And then every time you do see a junction, it's obvious that they're not connected, and if they do need to be connected, we separate them around. So just a word about this. Back to this specific problem. If I now want to have technology mapping into NAND gates, I do need to start putting the bubbles around. So let's see what changes I do need to make for this circuit. Luckily, it's a bit neater because it's right here on the screen. I didn't draw it. But in order to make this OR gate an AND gate, I do need to introduce bubbles at the entrance to the inputs, and I do need to counter them on the other side. Now, because I put a bubble here and there's nothing actually on the other side except the actual signal, I will put an inverter there. the bottom bubble, can be countered by putting a bubble here, which makes this an NAND gate. The next one is fairly easy. You just put the bubbles, no problem. For this OR gate, this bubble is not a problem. This one here, if I need to account for it, then I need to counter this signal coming here. I don't want to counter it before it goes into this gate, because then I have to mess around with this input. So I will add the inverter after the signal has split out. So I will put the inverter there. So doing all of these, and then I think there's a couple more. There's this, because I do want everything to be as NAND. I will put an inverter here. And for this one, I could actually, instead of inverting it, because I'm already inverting the signal D, I will actually cross this line and connect this. And I will show you this in a nice form in a second that I prepared earlier. But I can connect this signal to node D instead of introducing another inverter again, which gives me this result here, only nicer. Now all the places the ORs are now have their inputs inverter. I can just convert it into NAND gates, all of these ones. The NAND gates, well, the AND gates only turn into NAND gates. And the only thing that I want to show you now is this one here. So I'm taking a signal, I'm inverting it, and then I'm inverting it again. So there's, in a way, no point for these two inverters. I do need this inverter for here, but then, similar to what I've done there, I can cut this line out and then connect it directly to here, which then eliminates this inverter there. Now putting it nicely, so this is the line that I cut out, and I connected here, and I changed all of my ORs with their inputs inverted into NAND gates. Yeah?
Do inverters not count as outstanding?
So the reason why I've actually left the inverters here is just to save up a bit of a mess. The inverters will be implemented as a NAND gate with the two inputs tied together. Thanks for that. So every time you see an inverter, it is really an NAND gate implementation for an inverter.
If you want us to draw it, if we get a question like this.
If you leave it as inverters, I'll be more than happy. In fact, in reality, an inverter, when you actually look at the CMOS implementation of these things, and we will look at it in week 12, an inverter essentially is just an NAND gate with one input. It's pretty much the same idea when you implement it. So leaving it like this is actually all right, and calling it an NAND gate with one input, which is a bit of a funny one, but it is essentially correct. So yeah. All right. Any questions about technology mapping or design process or anything before we move on? All right.